Hello, my name is Girada Mihaiță Constantin. I'm a PhD student at University Politehnica of Timișoara under the advisory of Professor Nicolae Muntean. I work with this research group since 2018. My research is focused on power electronics, especially on DC-DC converters for microgrid and EV applications. I am working also in the automotive industry since 2017 as a hardware engineer developing onboard chargers. In this video, I will finish the presentation on hybrid DC-DC converters with improved bidirectional topologies. For this presentation, I prepared three hybrid bidirectional DC-DC topologies. I will start with the improved bidirectional hybrid switch capacitor converter and the improved hybrid switch inductor converter, where I will present the steady-state analysis, operation, and component design guidelines. Then I will present our motivation for developing these two converter structures that were used in a real-life application. In the end, I will present the experimental implementation and results for these two topologies. The third structure that I am going to present today is the common ground bidirectional hybrid switch capacitor converter. For this converter, I will present the steady-state analysis, operation, and component design together with the dynamic analysis and some experimental results. The first topology that we are going to cover today is called an improved bidirectional hybrid switch capacitor converter. The baseline for this new converter is represented by the topology that my colleague then presented in his previous lecture. This converter has some advantages such as wide voltage ratio, small passive components, and low active switch stress compared to other high gain converters. But the biggest disadvantage is given by the high frequency voltage between inputs. That is going to damage the EMI performance of this topology. Another disadvantage is given by the difficulties for a good layout implementation for the same reason stated before. For the improved version of this converter, these two inductors were split, separated, and connected to the negative outputs of the converter to eliminate the high frequency voltage between inputs. The change in structure does not reduce the performance of the initial bidirectional hybrid switch capacitor converter, and the inductor design can be made in a similar fashion. In the end, we have the following additional advantages. We achieve DC voltage between inputs. We have a lower volume of magnetic components due to the fact that these two inductors now are split and coupled, and we have a simplified manufacturing by using half bridges. This third advantage is going to be presented in the experimental implementation chapter of this converter. Here we can see the two equivalent schematics for the turn on and for the turn off phases. Firstly, we need to define some common assumptions in order to simplify the steady-state operation analysis. The converter operates in steady state, so the average voltage through the inductors are zero. We have a continuous conduction mode, all components are ideal, and capacitors C1 and C2 are equal. The two switches connect in parallel the capacitors from the switching cell during turn-on interval, in which the inductor current will increase in the buck mode. The switching cell is connected in series during turn-off interval, the interval in which the inductor current will decrease. In the first schematic, the capacitors are in parallel between the two voltage sources during turn-on interval, and during turn-off interval, the two capacitors are connected in series through the high voltage source. It can be observed that in buck mode, the two capacitors are charged in parallel and discharged in series, thus halving the voltage, and in boost mode, the two capacitors are charged in series and discharged in parallel, thus achieving a voltage doubling effect. The duty cycle is defined as the ratio of the turn-on interval and the total switching time. From all of the assumptions stated before, we can calculate the inductor's voltage, and then by applying inductor volt second balance, we can calculate the voltage ratio. We can see that this voltage ratio is bigger than a conventional buck boost converter. Because we have a switch capacitor structure, we can calculate the voltage of this capacitive cell, and we see that this value is equal to the voltage stress on switches S2 and S3. From the conventional buck, we know that the high side switch voltage stress is equal to Vin. In our case, high voltage source. So we can conclude that the voltage stress of the active switches on the proposed topology is lower than the one on the conventional buck. In here, we can observe the main theoretical waveforms of the proposed topology. We can see the inductor voltages here. We can see the voltage stress on the active switches. It can be observed that the current through switch S1 is the double of the current of switches S2 and S3. This is very important and it will help us in designing the experimental implementation using half bridges. We can also observe that the current ripple on the switching cell is quite high. We don't have in these waveforms the current ripple on the input capacitance because they are small, because of the presence of the inductors at each input. And on the bottom, we have the voltage ripples on the switching cell and the voltage ripple on the input capacitances. For the inductor design, a method considering a current ripple percentage is chosen. The ripple percentage is defined as the ratio between the current ripple and the average current. The ripple percentage usually is between 20 and 40% in order to have a continuous conduction mode operation on the whole range of input-output voltages. Because we have the inductors coupled, we can observe that the inductance of this could be half of the conventional bidirectional hybrid switch capacitor converter. After we get the output currents, we can calculate the inductor value and the inductor energy. Here we can observe that even if the converter has a wider operation and two inductors, the total energy is the same as the conventional buck-boost converter, which is a positive aspect. Next, we can proceed with designing the capacitors. When designing the capacitor, we choose a very similar method as with designing the inductors. We choose the method of voltage ripple percentage of the capacitors, but this time this voltage ripple percentage is much more smaller than the current ripple percentage on the inductors. This voltage ripple percentage is between 1 and 3%. By writing the capacitor currents, we can see that the ripple on the switched capacitors are larger. This can also be seen in the theoretical waveforms, which will result in a larger capacitance for the switch capacitor cell. Then, after we get the capacitor values, we can calculate the capacitor's energies, and then we can calculate the total capacitor energy necessary for this converter. We can observe from this total energy from capacitors in this converter that this value is higher than the conventional buck-boost converter, but also this value is dependent on the total inductor ripple percentage. So if we choose a higher ripple percentage, then we get a smaller capacitor value. Next, we also have to take into account the switch requirements. Here we used nominal voltage stress that appears on the transistor and nominal average current stress. In other research, the peak or RMS currents are used, but because the peak current is related to the ripple percentage and we can control this ripple percentage by design, we can simplify the analysis by using the average currents. As we already saw in the previous slides, the voltage switch stress is lower for this converter than the conventional buck-boost converter, and the current stress is higher for the switch S1 but lower for the other two switches. When combined, the total switch stress is resulting in a lower active switch stress than the conventional buck-boost converter. Next, in a similar manner, we are going to analyze the improved bidirectional hybrid switch inductor converter. This new converter is based on the conventional bidirectional hybrid switch inductor topology, which was presented by Dan in his previous lecture. This converter has some advantages as wide voltage ratio, small passive components, and low active switch stress compared to other high gain converters. But as a major disadvantage, we see that the voltage oscillations on the two inductors during turn on. Because of these oscillations, the voltage and current stress on the semiconductors will be increased, while the EMI performance of the converter will be lowered. The proposed improved bidirectional hybrid switch inductor converter will eliminate the voltage oscillations on the inductors during turn on while having additional advantages such as elimination of the high frequency voltage between inputs and minimization of parasitic switching inductance. While we can also make this topology using half bridges, which will help us in making a faster prototype. As a further improvement for this topology, we can get rid of the two capacitors placed at the inputs and furthermore make a coupled inductor for the switched inductive cell. Using this approach can lead us to have an even lower volume of the passive components, thus achieving the best power density possible out of this converter topology. Here we can see the two equivalent schematics for the turn on period and for the turn off period. During the turn on period, switches SH1 and SL2 are turned on and switches SH2 and SL1 are turned off, so that L1 and L2 inductors are connected between the high voltage source and the low voltage source. During turn off, switches SH1 and SAL2 are turned off and switches SH2 and SL1 are turned on. So the inductors L1 and L2 are connected in parallel through the low voltage source. The duty cycle is defined in the same manner as we defined it in the last converter. We are using the same common assumptions in order to simplify the steady state operation analysis. The converter operates in steady state, so the average voltage to the inductors will be 0. We have a continuous conduction mode operation. All components are ideal. And lastly, inductors L1 and L2 are equal, and the currents through L1 and L2 are equal, and capacitors C1 and C2 are equal, and the voltages on the capacitors C1 and C2 are equal. So we can calculate the inductor voltages, and then applying inductor volt second balance, we can calculate the voltage ratio, and we can observe that this voltage ratio is bigger than in the conventional buck boost converter. In here, we can observe the most representative theoretical waveforms for this bidirectional hybrid switch inductor converter. We can see the voltages on the inductors that are equal. We can see that the currents through the inductors are equal. The voltage stress on all four switches are equal. These four parameters are very important for us for defining the experimental implementation of this converter, because we see that we have the voltage stress equal on the active switches and the currents are equal through the inductors, and the inductor current is actually the switch current. We can implement this using two half bridges having the same semiconductors on each half bridge. Next, we can design the inductors in a similar manner in which we design the inductors for the bidirectional hybrid switch capacitor converter using a current ripple percentage. The ripple is chosen between 20% and 40%. After we get the output currents, we see that the inductor current is actually smaller than the low voltage side current, and this will help where we have applications where we are required to have a very large current on the output, because we can design those inductors to have a lower current, and in this way they are more easy to manufacture. From this output current we can calculate the inductor's values and energy, and we see again that this total inductor energy is equal to the conventional buck-boost converter, or equal to the bidirectional hybrid switch capacitor converter, even though we have different topologies. In this slide, the capacitor design is presented. We designed this capacitor in a similar manner to the previous converters using a voltage ripple percentage, which is between 1 and 3%. For these converters, we actually have two methodologies of designing the capacitor. The first methodology, which is presented in this slide, is using CH and CL capacitors. Using this approach, C1 and C2 values are small and can be neglected from the capacitor design. By writing the capacitor currents, we can calculate the capacitor values, and after that we can calculate the capacitor's energies. Finally, we get the total capacitive energy, which in the end is smaller compared to the conventional buck-boost converter, even though the current ripples are higher on this topology. The second approach that we can make in order to design the capacitors for this bidirectional hybrid switch inductor converter is to design our converter without CH and CL capacitors. This is needed in the applications where we want to have the best volume. C1 and C2 can be calculated using the same approach as in the previous slide, and we will get the following capacitors values. And the capacitor energy using C1 and C2 in place of CH and CLow is actually the same as in the previous design. So in the end, this is preferred in order to have the best volume possible. Next, we can calculate the total active switch stress for this topology. We can see that using this topology, we will have a higher voltage stress on all the switches, but a lower current stress. So in the end, calculating the total switch stress for this topology will result in a smaller active switch stress than in the conventional buck-boost converter, and the same active switch stress as in the converter previously presented, the bidirectional hybrid switch capacitor converter. As I said in the beginning, this topology has many advantages, but the biggest drawback is represented by the oscillations that appears during turn on the inductive cell. These oscillations will add additional stress on the semiconductors, and they will greatly damage the EMI performance of the converter. Previous research on this topology proposed methods to eliminate the voltage oscillations by designing a passive snubber. Adding a passive snubber will eliminate the oscillations during turn on, but it will damage the total efficiency of the converter. In this family of topologies, the oscillations are caused by the parasitic capacitors of the transistor in the switching cell CSL1 and CSL2 and the small differences between the switched inductances. The voltage on each transistor will oscillate around the theoretical level with the amplitude and frequencies depending on the values of the resonance circuit. The improvement proposed of this converter consists of adding the capacitors C1 and C2 and an additional switch which will eliminate the voltage oscillations by setting a constant voltage between the two sources VH and VLow with the value equal to C1 or C2. Here on this slide, on the left, we can see the simulation results for the unimproved bidirectional hybrid switch inductor topology without the added capacitors. We can see that we have present the inductor voltage oscillations as discussed in the previous slide. These inductor voltage oscillations will give us some semiconductor oscillations, and because of these semiconductor oscillations, we need to add the additional snubbers which will result in a lower efficiency for this converter. On the right, we have the simulation results for the proposed bidirectional hybrid switch inductor converter in steady state. We see that we have no voltage oscillations on the two inductors L1 and L2 compared to the conventional structure. Because we don't have any voltage oscillations on the inductor, it can be derived that we don't have any voltage oscillations on the semiconductors. And thus, we can remove the snubbers. Here on the bottom, we have the simulation for transient operation mode, which presents a stable operation with a simple PI controller controlling the current through the coil L1, with a fast transition between buck and boost operation. A small damped oscillation is present in the second inductor current, EL2, which can be ignored or it can be eliminated using a different control strategy. Next, in this slide, we have the steady-state experimental results for the proposed bidirectional hybrid switch inductor converter presented for a step-up operation mode. The results for the step-down operation mode are very similar. The converter was built with the parameters inside this table, having connected at each output two resistors. For the high voltage input, we have R load H, and for the low voltage input, we have R load L. The inductor voltages and currents for the step-up operation mode are presented in these waveforms and show no oscillations and are in concordance with the actual simulation results. On the right, we have the voltage on switches VSH1 and switches VSL1 together with the two complementary driving signals VPVM off and VPVM on. As the voltage on the inductors does not present any oscillations, the same is valid for the transistor voltages. In the end, we can conclude that The experimental results for steady-state operation for both step-up and step-down modes are presented here, and neither presents oscillations and are very similar to the simulation results and the theoretical assumptions. In the following slides, I will present our motivation for developing these two converter structures. It is very important to remind you all that both converter topologies presented in the previous slides can be implemented in an experimental mode using only half-bridge configurations for the semiconductors. The motivation behind developing these two converter topologies was given by a project in which we implemented an energy conversion system for an electric city bus. The project goal was the development of a reduced scale, reduced power laboratory demonstration model for an urban electric transportation energy conversion system using supercapacitors as the main energy storing devices and a super high torque power density interior permanent magnet synchronous motor drive as the electrical drive. The energy conversion and storage system is composed of the bidirectional DC-DC converter and supercapacitor unit, the backup battery module, and the electric drive. The energy conversion and storage system is operating in three modes: charging, driving, and regenerative braking. In charging mode, the energy conversion and storage system is connected to the charging station here. The supercapacitors are charged fast at the maximum allowed current, controlled by the bidirectional hybrid DC-DC converters. In driving mode, the energy conversion and storage system is disconnected from the charging station. Therefore, the energy is being taken from the supercondensators through the bidirectional hybrid DC converters and delivered to the electrical drive. In this mode, we may not use all the converters in parallel if we need only a reduced power. During the regenerative braking periods, the energy is taken from the electrical drive through the bidirectional DC to AC converter and transferred to the DC voltage bus. We developed prototypes for both topologies, the improved bidirectional hybrid switch capacitor converter and the improved bidirectional hybrid switch inductor converter that was presented by me in the previous slides. The main idea in the implementation was the use of half-bridge modules. By using half-bridge modules, the manufacturing process of the converter is improved, and the parasitic inductances are reduced in the switching loops. GaN switching devices were used in order to achieve better efficiency. The half-bridge modules, the improved bidirectional hybrid switch converter, and the new bidirectional hybrid switch inductor converter experimental modules are presented in the following slides. Here on this slide, we can see the two half-bridge modules that we have developed. The first half-bridge module that we are going to cover is this one. This one is using an enhancement GaN from GaN Systems, and the module is developed using two PCBs. The first PCB is an IMS PCB. On the IMS PCB, we have placed the power connections and the transistors here and here, and we have placed the DC-link capacitors. The DC-link capacitors are Serlink from TDK. We have chosen this capacitor because it has a similar capacitance as the ceramic capacitors, but the similar capacitance is achieved with a much lower volume. So choosing this CeraLink will give us a better power density. On the normal FR4 PCB, we have the gate drives and gate drive supply. Those gate drives are isolated. And we have two more DC-link capacitors if needed. The main parameters of this half-bridge module that is using the GaN system transistors are here. We have a drain voltage of 650 volts, an RDS on of 25 milli, drain current of 60 amps, a reverse recovery of 0 nanocoulomb because of the enhancement GaN, and a gate charge of 14.2 nanocoulombs. The second module that we developed is using a different type of GaN transistor, a depletion GaN transistor. The manufacturer of this transistor is Transform, and this is the part name. And we can see here that this half-bridge module is using only one PCB, only one simple FR4 PCB, because those transistors are in TO247 packages, and we have the same components. We have the gate drives, isolated gate drives with isolated supplies. We have the DC-link capacitors, the same from CeraLink. We have the power connections, and we have the transistors on the bottom placed directly on the radiator. Here we have the signal connector. The main parameters for these half-bridge modules with the transform GaNs are here. Again, drain to source voltage of 650 volts. The RDS on is a little bit higher, 41 milli. Drain current 46.5 amps. And the reverse recovery is 150 nano because of this different topology of GaN transistor. The gate charge is a little bit bigger than the GaN system because this transform GaN is in a TO247 package, which is not the best package for a fast switching device. Next, on this slide, we can again observe the improved bidirectional hybrid switch converter. Taking a look to this topology, we cannot easily see how we can connect this topology using half-bridge modules, because one half-bridge module consists of two semiconductors, two half-bridge modules consist of four semiconductors, and in this topology we have only three semiconductors. But we need to remember that the current through this switch S1 is actually double the current of switches S2 and S3. And if we take a look, the source here is connected to the drain, and then the source here is connected to the drain. So we may have a chance to develop this converter using half-bridge modules. So we came up with this arrangement that is using two half-bridge modules, and for the switch S1 we connect S11 and S12 in parallel because we have double the current of S2 and S3, and in this configuration we are using four semiconductors of the same type. And here we can see the photo of the converter. We can see the high voltage side inductor, coupled inductor. We can see four leads. We can see the low voltage side coupled inductor, the current sensor, the voltage sensors, and we can see that we have a couple of spaces in the PCB where some electrolytic capacitors could be placed. Those spaces are actually in here for the switched capacitor cell, but we discovered during our testing that these electrolytic capacitors are not needed because we can manage to have this switched capacitive cell with only the Serra-link capacitors, the DC-link capacitors placed directly on the half bridges, here C2 and C1. We can do this because of the increased frequency in which we are operating. The main parameters for this converter are here in this table. We see that we have a high voltage side with a voltage of 400 volts. We have a low voltage side with a voltage of 0 to 160 volts. This is actually the supercapacitor voltage. We have a operation frequency of 200 kilohertz. The power level is around 6 to 7 kilowatts. For the inductors, we have custom-made these inductors using distributed air gap cores from Magnetics. These are powder cores. And the capacitor used, as I said, are Serra links here and here. And for the transistors, we have chosen to go with the transform module because the frequency is not that big. And these half-bridge modules are actually more economically correct because they are using only one PCB and the transform packages are cheaper to buy. On this slide, I will present the experimental implementation of the improved bidirectional hybrid switch inductor converter. We can see that we have two half bridges. The first half bridge is formed out of SH1 and SL1. This half bridge is connected between the two sources. We have here the positive terminal of the high voltage source and the negative terminal of the low voltage source. Between them we have the first half bridge, and the C1 is the DC-link capacitor. The second half bridge is formed out of SH2 and SL2. The SH2 is connected to the positive terminal of the low voltage source, and the SL2 is connected to the negative terminal of the high voltage source. And with C2, they are forming a half bridge module with a DC-link capacitor. We can see here on the bottom the photo of the experimental implementation of the bidirectional hybrid switch inductor converter. We see that we have used the same half-bridge modules that we have used in the bidirectional hybrid switch capacitor converter. These half-bridge modules are done with the transform gun. We see the DC-link capacitors, Serra links. We see the coupled inductor L1 with L2. They are coupled on the same magnetic core for achieving the best power density, and as well as on the bidirectional hybrid switch capacitor converter, we see some capacitor footprints, electrolytic capacitor footprints here and here, but they are not placed because we discovered that these Serra link capacitance are enough for a good operation of this bidirectional hybrid switch inductor converter. The parameters can be seen in this table. The input-output parameters are the same as with the bidirectional hybrid switch capacitor converter, with the high voltage input source of 400 volts, the low voltage input source from 0 to 160 volts, which represent the supercapacitor voltage. The power level is again the same, between 6 to 7 kilowatts. The frequency is 200 kilohertz, the same. And the coils are made with the same type of distributed air gap cores from Magnetics with powder cores. And the capacitors are still the same, Serra links from TDK. Next, in this slide, I am going to present the experimental results for the improved bidirectional hybrid switch capacitor converter. The experimental results are presented for the following parameters. The high voltage supply voltage is 375 volts. The low voltage supply is 80 volts. This is actually the supercapacitor voltage, and this parameter will vary a bit during testing. And the low side current, or the current through the supercapacitor, is 22 amps. In this first waveform, I'm going to present the inductor current and voltage waveforms. We have the voltage and current for one winding of the coupled inductors at each input. So we see that we have no current oscillations on the coil or no voltage oscillations on the coils, neither on the high voltage input coil or the low voltage input coil. Next, in these two waveforms are present the current and voltage of the coupled inductors. So here we have the L1 inductor current and voltage, and here we have the L2 inductor current and voltage. We can see that we have an almost perfect match between the voltages and the currents for both inductors. So we can take the conclusion that the coil designed for this converter is done properly. In the last waveform, we have the capacitor voltage ripple waveforms. With blue and green, we have the input and output voltage ripples, and with magenta and yellow, we have the two capacitors placed across the half bridges. We see that we have no major oscillations on these ripple voltages on the turn on or turn off period, neither on the switching time. We continue with this slide, the experimental results for the improved bidirectional hybrid switch capacitor converter. We see in the first waveform the transition from buck to boost. In the waveform are present the inductor current and output voltages. It can be observed that we have a fast transition without any overshoots or undershoots. In the second waveform, we see the same thing, but now the transition is done from boost to buck, and we see that we have similar results, good results, a fast transition from boost to buck without any overshoots or undershoots. So we can conclude that our regulator design is properly designed. In the last waveform that I'm going to present for this converter, we can see maybe the most representative waveform for this topology, which are the voltage between inputs. I said in the beginning, this improved version of the bidirectional hybrid switch capacitor converter has no switched voltage between inputs. So we measured the negative terminal from the low voltage supply and the negative terminal from the high voltage supply, and the positive terminal from the high voltage supply with the positive terminal from the low voltage supply, and we see that we have an almost DC voltage between inputs. So this is good because it will improve our EMI performance, and with the improved EMI performance we have an improved overall converter performance. I will finish my presentation with the third and last topology. This topology is entitled the Common Ground Bidirectional Hybrid Switched Capacitor Converter. The Common Ground Bidirectional Hybrid Switch Capacitor Converter is derived from the unidirectional variant of this topology that can be seen here on the left picture. Also, this topology is derived from a conventional buck converter in which a switched capacitor cell was inserted at the input. A difference between this common ground bidirectional hybrid switch capacitor converter and other switch capacitor or switch inductor topologies is that this topology will achieve a common ground between the high voltage source and the low voltage source during its operation. So during turn on or turn off, the ground from the high voltage source to the ground of the low voltage source is not interrupted. As main characteristics of this converter, we can say that we have a high conversion ratio. We are required to have only one driving signal, and we have this common ground. The main components of this converter are those 5 switches, the 2 inductors at each input, and the 4 capacitors, the switch capacitor cell and the input capacitor and the output capacitor. Next, we can see the two equivalent schematics for the turn on phase and for the turn off phase. The operation of this converter is very similar to the operation of the conventional hybrid switch capacitor converter that was presented earlier. We define the same common assumptions in order to simplify the steady state operation analysis. So, the converter operates in steady state, so the average voltage through the inductor are 0. We have a continuous conduction mode. All components are ideal, and the capacitors C1 and C2 are equal, together with the voltage across these two capacitors being also equal. This converter can be seen either as a buck converter if we are looking from VH to VLOW perspective, or as a boost converter if we are looking from VLOW to VH perspective. The switch capacitor cell, therefore, is connected at the input of a buck converter or at the output of a boost converter. In buck mode, the two capacitors from the switching cell are discharged in parallel to the low voltage source during turn on. The current also charges these two capacitors, but the value is much lower than the discharge current, so this value can be neglected. The capacitors are then charged in series from VH during turn-off period. In this way, we can obtain a halving of the voltage. In a similar manner, we can analyze the boost operation mode, where the capacitors are charged in series and discharged in parallel. In this way, we can obtain a doubling effect of the voltage. The duty cycle is defined similarly as we did with the other two converters, as the ratio of the turn on by the total switching time. From all the assumptions stated before, we can calculate the inductor voltages, and then by applying volt-second balance, we can calculate the voltage ratios. We see that this voltage ratio is bigger than a conventional buck boost converter, and because we have this switch capacitor structure, we can calculate the voltage on this capacitive cell, and we see that this value is equal to the voltage stress on switches S3 and S5. And because we know the voltage stress on the conventional buck converter or boost converter we can say that these voltage stresses on this bidirectional hybrid switch capacitor converter with a common ground are lower than the one of the conventional buck boost converter. In this slide, we can observe the main theoretical waveforms for this converter, which are similar to the waveforms in the other two converters presented before. We have here on the top the voltage across the two inductors. We have the current through the two inductors. We have here the current on the switch capacitive cell and the voltage on the switch capacitive cell. The last two waveforms are representing the ripple voltage for the input and output capacitors and the ripple voltage for the switched capacitor cell. We come again to the inductor design for this bidirectional hybrid switch capacitor converter with common ground. The inductor design is done in a similar manner to the other converters by choosing a current ripple percentage. This current ripple percentage is between 20 and 40%. And we can get the inductor values and then in the inductor energy. Here we can observe that even if the converter has a wider voltage operation and two inductors instead of one, the total inductor energy is the same as the conventional buck boost converter, which is a positive aspect. We also need to design our capacitors in this topology. This capacitor design is done in a similar manner to the previous converter using a voltage ripple percentage which is chosen between 1 and 3%. By writing the capacitor current, we can calculate the capacitor values, and after that we can get the capacitor's energies. Finally, we get the total capacitive energy, which in the end is the same as in the conventional buck boost converter. This result is a positive one because this bidirectional hybrid switch capacitor converter with the common ground has an improved conversion ratio. The last design parameter for this converter is represented by the total switch stress or the total stress on the semiconductors. We calculate the switch stress in a similar manner as we did for the other two converters, and we already saw in the previous slides that the voltage switch stress is lower for this converter in comparison to the conventional buck boost converter. And from the current stress, we get the total switch stress, and we see that even though we have 5 semiconductors instead of 2 on this topology, the total switch stress equals to a lower total switch stress compared to the conventional buck boost converter. Because this topology has a larger number of passive components, therefore is a higher order system, it is important to analyze the stability by mathematical and simulation means prior to the final design stage. In order to make the stability analysis, the state space average method is used. In order to obtain the mathematical model, the equivalent schematic, including all of the parasitic resistors on every semiconductor, every capacitor, and every inductor, is present in this drawing. The following hypotheses are considered valid for the stability analysis. So, the power switches devices S1 to S5 are ideal switches in series with parasitic resistances. The VL and VH have a constant value during one switching period. L1 and L2 have the parasitic series resistances RL1 and RL2 respectively. C1 and C2 have equal parasitic series resistances RC1 equal to RC2 equal to RC. Cl and Ch have the parasitic series resistances RCl and RCH respectively. The two equivalent switching schematics are presented here. On the left, we have the equivalent schematic for the turn-on period, and on the right, we have the equivalent schematic for the turn-off period. Considering the state x and the input u vectors, the state space representation for the two switching period can be explained as in this equation, where I is 1 for turn on and 2 for turn off. According to the state space average method, the state space representation of the equivalent average model of the system is given by this equation, where the matrices A and B are obtained from AI and BI through a weighted summation where I is equal to 1 for the turn on period and equal to 2 for the turn off period. The average converter model, whose state equations are described in this equation, is also valid if the duty cycle changes slightly around the steady state value of D. Linearizing the system around a steady state duty cycle D for a small signal variation will give us the following system, with the equivalent matrix described in this equation. The CE matrix can be either 1, 0, 0, 0, 0 or 0, 1, 0, 0, 0 in order to express the desired transfer function for one of the two inductor current, which are needed to control the bidirectional converter. The above-mentioned transfer function can be obtained by solving this following equation. The Bode diagrams of the two transfer functions are presented in this figure. We have displayed in this Bode diagram both transfer functions for the two inductor currents that we want to control. We see that we have also displayed in this Bode diagram the PESIM simulation results. The results show a very good correlation between the two models, meaning that the mathematical model, which is calculated very quickly, is sufficient for a good controller design and analysis. Even if the PESIM simulation model should be more close to the real converter, it has a much slower simulation runtime. The block diagram of the control loop is presented in this figure. The transfer functions are discretized with a zero-order hold method, and a supplementary time delay is added to take account for both the PWM and ADC's delay. The discrete transfer functions are presented in this Bode diagram. The diagrams of the transfer functions obtained through the state space average method are compared with the diagrams obtained to the digital simulation, resulting in an unnoticeable difference between them. The component values and parasitic resistances values used in the calculation of the two transfer functions are given in this table, and they are catalog data values of the real components used in the bidirectional hybrid switch capacitor converter with a common ground prototype that is presented in the following section. The current through coil L1 was chosen as a control variable as it has a larger value than the current through the coil L2. A digital current controller was designed for the overall system stability based on H1Z transfer function. The transfer function of the controller is given by this equation. The Bode diagram of the transfer function of the converter with the controller is present in this figure. The frequency response shows a good stability due to the displayed phase margin of 80 degrees at the crossover frequency of 1.29 kHz. This converter was developed for a demonstration site of a DC microgrid implemented into an experimentarium module. This module will be presented in detail by my colleague Danut in a future lecture. The main demand for this application was to have a converter that is connecting the 350 volts DC bus to the 24 DC bus without having an interruption on the ground path. And that's why this proposed topology fits the best in this application. In this slide, we have a picture of the experimental module of this bidirectional hybrid switch capacitor converter with a common ground. The main parameters can be seen in this table on the right. We have a power of about 3.25 kilowatts. We have the low voltage between 0 and 80 volts. The high voltage is 325 volt, and the operation frequency it's 80 kilohertz. These are the switch capacitors C2 and C1. This is the inductor L2. Those are the capacitors at the input, at the high voltage input. These are the capacitor at the low voltage input. And this is the coil L1. We see here the current sensors. We have also voltage sensing placed on the bottom, and the switches are placed here on the bottom, the 5 switches, and they are GaN switches, depletion mode GaN switches from Transform. They are similar with the switches that we implemented in the 2 other topologies. So prior to placing this bidirectional hybrid switch capacitor converter with a common ground in the experimental module, in the experimental house, we tested it in our laboratory. So here on the right, we see a block diagram of the test system, and on the left, we see the actual picture of the test setup that we have used. We have here the bidirectional hybrid switch capacitor converter. We have here on the bottom the 2 supercapacitors that we have used as a low voltage source. Then we have here the high voltage source that is in parallel with a constant voltage electronic load. And we have here the 24 volt supply used for control. The first test that we run with this bidirectional hybrid switch capacitor converter are done at around 1/3 of the maximum power. Here on the left, we have the step-down operation of the converter. The high voltage is 300 volts, the low voltage side it's 80 volts, and the current is 10 amp. We can see in this picture the semiconductor drain to source voltages, and we can see that we don't have any major overshoots on the drain. We have placed only small snubbers on the semiconductors on this topology. Here on the right, we have again the step-down operation at 125 volts, the high voltage side, 40 volts, low voltage side, and the current again, 10 amp. And we have the voltage across the switch capacitor cell. We have the PWM driving signal, and then we have the two inductor currents. We can see that we have a good operation without oscillations on the voltage across the supercapacitor cells and without major oscillations on the uh, inductor currents. In this waveform, we have present the waveforms for a step-down operation at 300 volts for the high voltage source, 80 volts for the low voltage source, with the inductor current controlled at 10 amp. We see in channel 1 the voltage on the inductor L2. On channel 2 we see the current through the same inductor. On channel 3 we have the voltage on the inductor L1, and on channel 4 we have the current through the inductor L1. We see that we don't have any major oscillations. We have some during turn on period on this current, which is not controlled, and we have some overshoots on the inductor, but nothing major. The converter operates in good conditions. The last waveforms that I'm going to present for this converter are represented by the dynamic results of the controller. We have on the left a transition from buck to boost, and on the right a transition from boost to buck. The transition is done at 10 amp, so we have 10 amp here and minus 10 amp here, or 10 amp here and minus 10 amp here. We see that we have quite fast transition with some damped oscillations on the transition side, but nothing to worry about. And here on a different transition, it's the same thing, some damped oscillations, but nothing to worry about. We can conclude that our controller design is performing quite good, and this is sufficient for our type of application. So in conclusion, we can say that overall the hybrid converters have a good characteristics and are a good choice where a wider conversion ratio is required. In this lecture, I presented 3 new topologies. Out of these 3 new topologies, 2 of them are being improvement version of our prior topologies, solving the problems that we discovered during the years that we worked with these topologies. So we can say that those improved versions are real mature now. And again, I presented 2 real life applications. From this, we can say that these hybrid converters are actually usable into multiple application types. So I put in here the most relevant references for this lecture. Thank you for your attention. This was my presentation on the hybrid bidirectional converters with a practical approach. I hope this presentation was helpful for you, and I am glad that I had the chance to share with you our years of knowledge and development on the hybrid bidirectional converters. I wish you all the best, and hopefully we can collaborate soon on future work. Goodbye.